adding or subtracting the degrees of turn to roll out. Lag and lead can be minimized by making very shallow banks. If you limit banks to half standard rate or less, the compass seems to be more truthful. After attempting to use the compass to turn to headings, pilots become much more enthusiastic about perfecting timed turn technique. For most of us, timed turns work out much better than compass turns. Another trick to use, if a level turn is through east or west, is to time the turn on those headings. The compass is believable on those headings, giving us a reliable intermediate point from which to measure time. Beyond the flight test, you may have other tools in the cockpit available for heading control after the loss of your heading indicator. In the event of an actual failure, many dedicated aviation apps can display backup flight instruments when connected to an external receiver. These portable receivers include GPS and electronic accelerometers and magnetometers to provide instant pitch, bank, and heading representations on your tablet. The track indication on your installed or handheld GPS can also provide an emergency backup. This ground track information can be easier to interpret and to use than the magnetic compass. If you decide to use this indication during an emergency, inform ATC. This will allow the controller to take out the wind correction normally added to heading assignments. Hopefully, you'll never be forced to fly partial panel. Pump and instrument failures do occur, so it's best to be prepared. Remember, the principle of insurance is protection against events that rarely happen, but could be catastrophic when they do. The cheapest insurance you can have is to maintain your proficiency on partial panel. It's more work, less fun, and can be downright embarrassing, but it'll be worth every moment you spend when and if any instruments go belly up.
To the right. An airplane doesn't. An unusual attitude is any attitude not normally required for instrument flight. This can result from turbulence, disorientation, confusion, or failure of an instrument or instruments. When instruments indicate an unusual attitude, it's important to decide whether there's been an instrument failure, and if there is, whether or not the airplane really is in an unusual attitude. The correction of instrument indication, abnormal indications, or excessive rate of movement call for increasing the cross-check, verifying whether it's really an unusual attitude or an instrument malfunction. Based on the indication of this airspeed indicator, the pilot should reduce power, level the wings, and raise the nose. Now, after checking the other instruments, it's apparent that the airplane is in a nose-high turn to right. The altimeter and vertical speed indicator both show a climb. With the airspeed approaching the never-exceed airspeed, the altimeter and vertical speed indicators should indicate a steep descent. The attitude indicator shows a nose-high bank attitude to the right. The right bank is confirmed by the heading indicator, which is showing heading changing to the right, and the turn coordinator, which shows either a turn or a roll to the right. After checking the other instruments, what at first glance appeared to be a nose-low usual attitude is a nose-high climbing turn to the right. Both the pitot ram air input and drain are blind, which is causing the airspeed indicator to act as an altimeter. Up until now, you have been taught to have faith in your instruments. This is still true, but if the instruments do not agree, one or more of them must be wrong. Before we look at more situations of instrument or system failure, let's review the flight instruments and the systems that make them work. The pitot system is one of the inputs for the airspeed indicator. It is not an input for any other instrument. The airspeed indicator, altimeter, and vertical speed indicator use the static source. Vacuum or pressure operates the gyros for the attitude and heading indicators. In the usual arrangement, the turn indicator gyro is driven by electricity. In the illustrations that follow, the attitude and heading indicators are vacuum operated and the turn indicator is electric. It's relatively easy to determine if only one instrument has failed. For example, if all instruments show straight and level flight and the airspeed indicator is decreasing, then the airspeed indicator has failed, or the pitot system has become blocked. Another possible failure of a single instrument is the turn indicator, since it is electrically operated. By singling out the one instrument that does not agree with others, we can identify the failed instrument. However, if more than one instrument is failed, it may be a bit more difficult. Suppose that your instruments show this. The attitude indicator shows a bank to the right with a slightly nose-high attitude. However, the turn indicator shows straight flight, and the altimeter, vertical speed indicator, and airspeed indicator show level flight. Also, the heading indicator is turning towards decreasing numbers, and therefore is indicating a left turn. Which instruments have failed? The attitude indicator and heading indicator disagree with each other, as well as with the other instruments. Since we know that both of these instruments are operated by the vacuum system, it's probably a good bet that the vacuum system has failed. On the basis of the operating instruments, the airplane is in straight and level flight. A glance at this airspeed indicator would lead the pilot to add power, lower the nose, and level the wings to recover from an apparent nose-high unusual attitude. In fact, the airspeed indicator is showing a speed below the landing configuration stall speed. Before acting on the indication of one instrument, look at the other instruments. The other instruments disagree with the airspeed indicator. Majority opinion has the airplane in a level turn to the right. An airplane doesn't usually go instantly from stable flight to wildly divergent flight. If the airplane was in a normal pitch and bank attitude a moment ago, chances are that it hasn't diverged very far from that attitude. Take the time to check the other instruments.
If you let the changes pile up, it'll be like learning it all. There's more to getting an instrument rating than just flying the airplane. A lot of head work is needed.
To use instrument charts, the rules for IFR, and the procedures for operating in the air traffic control system. In this section, we'll review the various resources you should become familiar with to help you with your planning on the ground and navigating in the air. Let's start with navigation in the IFR en route chart, which is the instrument pilot's equivalent of a sectional chart. It's used for en route planning and depicts airports and airways. These are available as both printed large foldable maps and as a moving map layer in aviation apps. Then there is what is collectively called the Terminal Procedures publication, commonly referred to as approach plans, which is a large collection of individual charts and procedures designed specifically for an airport. Most of this resource is comprised of instrument approach charts, but it also includes IFR takeoff minimums, departure procedures, arrival procedures, and alternate airport information. In print form, all of this information for a specific state or states is in a single book. Most pilots prefer the digital version of these charts in an aviation, where they are better organized, easy to update, and display your airplane's position on the chart. Take some time to familiarize yourself with where each section of the TPP is located in your aviation. In ForeFlight, for example, the departure, arrival, and approach charts can be found in the plates section of the app. The legends, climb, and descent tables, however, are located in a separate supplement in the documents section of the app. Like with VFR sections, both the en route and terminal charts are updated every 56 days. When using digital IFR charts in an aviation, you'll see that the FAA version is displayed by default. Jeppesen produces their own version of IFR en route and terminal charts, which require an additional paid subscription. Jeppesen publishes charts for nearly every airport in the world, making them the preferred chart type for airline pilots and professional flight departments.
Next, we're going to look at several of the study resources and handbooks you need to reference during your training. A digital version of each of these is included with this course in the FAA Handbook section of the menu. First, there's the Instrument Flying Handbook, which covers everything from IFR rules to instrument flying techniques to instrument approaches. Next, you'll want to check out the Instrument Procedures Handbook, which goes into much more detail on departure and route, arrival, and instrument approach procedures. If you have a technical question related to a specific detail on an instrument approach, this is the place to go. There are a lot more rules governing instrument flying, and you'll be spending a lot of time both during and after your training referencing specific requirements. Remember, Part 61 covers topics like the requirements to earn an instrument, recent experience requirements, and logging of flight time. Part 91 is focused on general operating rules and includes things like equipment, flight planning, and inspection requirements. To learn more about air traffic control, communications, and instrument procedures, check out the Aeronautical Information Manual, or AIM. The AIM is designed to provide pilots with basic flight information and ATC procedures required to fly in the National Airspace System of the United States. And a lot of it was written specifically for instrument pilots. One thing to count on, there will be changes made in the rules and procedures. Individually, these changes may not seem significant, but over a period of time, the cumulative effect of these changes is substantial. You may wonder, how in the world can I keep up with all the changes? In the front of each print and digital issue of the AIN, there is a listing of major changes and the effective date. This listing gives a brief description of the changes. For details about each change, turn to the affected paragraph. The updated content is denoted by the black sidebar. Learning to use the IFR system is both challenging and fun. The more you know about the system, the better you'll be able to use it to your best advantage. After you know how the system works, take the time to learn the revisions. It's easy to keep up. If you let the changes pile up, it'll be like learning it all over again. The bulk of your IFR flight will be the en route phase, which requires careful consideration before departure. During your pre-flight planning, you'll want to spend some time determining the best route using GPS, VORs, and airways. There are a variety of FAA and third-party chart options available to help plan an IFR flight. For a big picture view, check out the IFR en route planning chart. Planning charts are useful for long-range planning on the ground, but do not give you the detailed information that's needed in the air while flying an IFR trip. Among other things, the charts show radio aids to navigation, airways, mileages on airways, and special use airspace. For a detailed look at IFR airways and routes, check out the IFR Low Altitude en route chart. This is the primary reference for getting details on low altitude Victor airways, which go up to, but not including, 18,000 feet MSL. It also depicts RNAV terminal transition routes, called T routes, in blue. The IFR high altitude en route chart is useful for flights above 18,000 feet. This chart depicts both jet airways based on VORs and RNAV Q routes, both of which extend from flight level 180 up to flight level 450. The FAA issues a new set of en route charts every 56 days in both paper and digital formats. Each chart features a legend, which is included in most mobile applications for reference. Many aviation mobile apps also include data-driven aeronautical charts with IFR navigation features depicted, which scale up or down automatically based on the zoom level. These are great for in-flight use while flying with a tablet, allowing you to interact with each VOR, airport, or intersection by tapping on the map. The downside is they typically don't include all the airway details, so you'll still want to reference the FAA's IFR and route chart when planning a flight along Victor Airways. Now let's examine some of the details on the IFR charts, starting with Victor Airways. Victor 2 is the straight line of airway between the Rochester and Syracuse vortex. In general, even-numbered airways run east-west and odd-numbered north-south. Victor 2 is the 279-degree radial of Syracuse and the 99-degree radial of Rochester. For flight planning, average the courses of straight-line airways. When flying the airway, use the charted radius. The 65 in the box is the nautical mile distance on Victor 2 between the Rochester and Syracuse vortex. The distance on the dogleg Victor 483 is 68 miles. Segment distances are printed either above or below the airway. From the Rochester vortex to north is 16 miles. Triangles are reporting points based on VOR or MDB airways. Black is used for those based on VHF-UHF facilities, like a VOR, and brown is used for reporting points based on low-medium frequency facilities, like an MDB. Blue stars are used for RNAV reporting points. Solid symbols are compulsory reporting points, and open symbols are non-compulsory on-request reporting points. Near Yakima Air Terminal, Pallister Field, there are examples of both compulsory and non-compulsory reporting points. Notice the Yakima vortex is also a compulsory reporting, as depicted with the filled-in vortex symbol. We've looked at the main features of the en route charts. There's a lot of other information charted. Take some time to become acquainted with the en route charts. Flying IFR is not the time to be studying charts and looking up information in the legend. There can be as many as 4 altitudes for an airway. Between Geneseo vortex and Beeps intersection, the minimum en route altitude, MEA, is published as 4,000 feet. The MEA meets obstacle clearance requirements, assures a satisfactory navigation signal, and the identification of fixes on the airway. You will sometimes find a lower altitude published directly below the brief with an asterisk. This is the minimum obstruction clearance altitude, or MOCA, 3,300 feet for this airway. Over non-mountainous terrain, the MOCA is at least 1,000 feet above the highest obstruction, within 4 nautical miles, until you again receive a navigation signal. And is a directional bound airway with a maximum authorized altitude of 7,000 feet. The short crossbars on each side of the airway bumps indicate that one or more of the airway altitudes changes. Eastbound bumps, the MEA changes from 3,000 feet to 3,500 feet. ATC may have an IFR airplane cross a fix beyond which a higher altitude is required at the altitude appropriate to the segment on which that fix is approached. Translated, this means that an eastbound IFR flight could cross bumps at 3,000 feet. The clearance to climb to the higher altitude can be issued as late as immediately after passing bumps. At Neola, on Victor 101, east of Salt Lake City, there is a minimum crossing altitude of 12,000 feet westbound. The MEA changes from 10,000 feet to 15,000 feet at Neola, and airplanes must be at or above 12,000 feet before proceeding west of Neola. Victor 187 west of Great Falls has bidirectional MEAs. From Great Falls to Rosso, the westbound MEA is 10,000 feet in anticipation of the next MEA of 13,000 feet. airplanes east of Rosso can be descended to the eastbound MEA of 8,000 feet. On a straight airway, changeover of navigation is usually made at the midpoint. In this case, the changeover point is not charted. If a straight airway changeover point is somewhere other than the midpoint, this symbol is used. On Victor 104, the VOR changeover point is 75 miles from Bangor and 25 miles from Berlin. A changeover on a dogleg airway is where the airway bends. On Victor 322, the changeover point is at Milo. Arrows are used to show how intersections are defined. Whiffing is defined as the intersection of the 279-degree radian from Syracuse and the 216-degree radian from Watertown. An open-headed arrow signifies DME distance as well as azimuth. The open-headed arrow at whiffing indicates the 279-degree radian of Syracuse and denotes that the DME distance is the same as the chart distance of 15 miles. Second and succeeding DME fixes show the cumulative distance. Congo is 24 miles from Syracuse. Blue and green airports have a published instrument approach available for civilian aircraft. Brown airports are charted for emergencies. They don't have a published approach, but do have runways at least 3,000 feet long. Low-altitude IFR RNAV routes are printed in blue and identified by the letter T and a 3-digit number. Mileages, GPS MEAs, and magnetic reference bearings are included. An IFR-approved GPS is required to fly these RNAV routes. Within each quadrangle of latitude, Global Positioning System, GPS, and the Wide Area Augmentation System, WAS, are part of the Global Navigation Satellite System, also known as GNSS. Avionics used to interact with the GNSS are often referred to as navigators. Older GPS-only IFR navigators are approved as a supplemental navigation system. This means that an alternative means of navigation for the route must be installed and operational. Modern WAS GPS navigators may be the sole IFR navigation source, but a backup is still a good idea. Both types of navigators allow random area navigation, or RNAV, permitting long direct IFR flights. Basic GPS uses a network of satellites to triangulate a position anywhere on Earth. There are at least 5 satellites in view at all times. By knowing the precise location of each satellite and reconciling timing with the atomic clock on the satellite, the navigator can accurately measure the time each signal takes to arrive. The navigator can provide 3-dimensional position and altitude information if it is receiving signals from at least 4 satellites. The signals are line of sight and virtually unaffected by weather. WAS uses 2 additional geostationary satellites to improve the accuracy of GPS in the National Airspace System. These satellites receive and transmit a correction signal to WAS-enabled navigators. The correction signals are calculated on the ground by 2 wide-area master stations and uploaded to the stationary satellites. These master stations receive signal error data from a network of precisely surveyed reference stations. The reference stations constantly monitor the GPS satellite signals for errors. WAS augmentation allows more precise locations in both the horizontal and vertical planes. The precision is such that it can be relied on for vertical guidance during approaches down to heights as low as 200 feet above the touchdown zone. If you were coming or going from a major terminal or flying in a congested area, like the Northeast or some areas along the West Coast, you may well have to still fly air rings, but once you are out in less traveled airspace, direct is the way to go. You should use charted fixes, VORs, intersections, or airports to identify the points between which you will be flying direct. Most of the airports in the U.S. have 1 or more GPS approaches. These often allow lower approach minimums than other non-precision approaches. If there's a departure procedure or star for an airport we're utilizing, plan on using it. They will be found in the database of the panel-mounted navigators that are approved for approaches. For en route operations, you can still file and fly long direct legs, but you do have to accommodate the terminal area requirements at the departure point, the destination, and at any busy terminals that might be along the route.
If air traffic control can't accommodate a long direct leg, they'll issue a full route clearance. Using some thought and preparation before filing your flight plan can reduce ATC changes to your route.
Be aware that unless you are flying on airways, no minimum altitude is published for the route. The IFR low altitude en route chart does provide an off-route obstruction clearance altitude, or a within each quadrangle of latitude and longitude. This altitude provides 1,000 feet of obstacle clearance in non-mountainous terrain and 2,000 feet of clearance in mountainous terrain, the minimum clearance required for filing IFR. It does not guarantee radio or radar coverage. A controller will not clear you to fly below a minimum sector altitude. Radar coverage is required. Each GPS installation must be FAA approved. The rules require you to have another form of navigation available to fly the approach at the filed alternate airport if the unit is a non-WASP GPS. For en route and terminal modes, you do not have to have a current database, but non-mountainous terrain and 2,000 feet of clearance in mountainous terrain, the minimum clearance required for filing IFR. It does not guarantee radio or radar coverage. A controller will not clear you to fly below a minimum sector altitude. Radar coverage is required. Each GPS installation must be FAA approved. The rules require you to have another form of navigation available to fly the approach at the filed alternate airport if the unit is a non-WASP GPS. For en route and terminals, you do not have to have a current database, but you do have to determine that the waypoints you use in the flight plan are current. A current database is required to fly GPS approaches. The navigator will not allow an approach if a feature called RAIN, Receiver Autonomous Integrity Monitoring, does not assure that the available satellite geometry will allow the receiver to calculate a position within a specified protection limit. RAIN needs a minimum of 5 satellites in view, or 4 and a barometric altimeter input from an altitude encoder. WASP navigators can utilize a WASP geostationary satellite as an additional pseudo-GPS satellite. Because GNSS navigators contain so much information and capability, you have to learn to use each unit. You should read the GPS manual and utilize available training software. The manuals and training aids are great for learning the switchology, but you do have to fly some flights and approaches with a GPS to really learn to use the navigator. It is generally required that both the flight manual supplement and the pilot's guide for the GPS navigator be available to the pilot whenever the equipment is being used under IFR. Always fly with a safety pilot when learning GPS because it requires a lot of heads down time. This should be done in VFR conditions. Let's look at some of the basics using a common GPS navigator, the Garmin GTN 650. If your training aircraft has another model, much of the information will be applicable, but you will also need to learn the nuances of your unit. The GTN 650, like its larger sibling, the GTN 750, is a WASP-capable navigator. These units primarily rely on a touchscreen interface to control and access information for the navigators, though it does have a few buttons and knobs. The best way to learn any navigator is through study and by methodically examining the results of each action. Using the GTN Trainer desktop or iPad simulator will be a big help here, since they allow you to practice using every feature of the GPS in a more relaxed setting. The small knob on the left side of the unit is used to control communication and navigation radio volume. The two buttons on the right side, Home and Direct to, offer shortcuts to the main menu and Direct to navigation feature. The GTN 650 also features two concentric control knobs at the lower right, which offer an alternate means to enter data into the system in addition to the touchscreen interface. When the 650 is powered up, it'll display the installed databases and expiration dates, along with a self-test page. Press the Continue button on each screen after verifying the information. One of the most commonly used functions is Direct. Press the button on the right side of the unit, and it'll ask you where you would like to go. Tap the Select Waypoint and use the on-screen keyboard to enter the airport identifier. If the airport has a 3-letter identifier and is in the contiguous 48 states, add a K to the front of the identifier. Don't add a K if the identifier contains numbers. The navigator is ready to take you there after a press of the Enter button to load the waypoint, and another press of the Activate button to fly the new course. To get your money's worth out of a GPS, though, you'll want to go beyond the Direct To function. The home screen of the GTN 650 is arranged with a collection of icons that take you to various pages of the GPS. Tap 1 to go to that page, and then use either the back button in the lower left corner of the screen or the physical home button at the top right to return to the home screen. Very similar to a smartphone. First, let's look at some of the available information in the default navigation screen. Some of the data is self-explanatory, like distance, ground speed, and estimated time en route to the next waypoint. Desired track is the course in degrees between the two active waypoints in your flight plan. Track is provided in degrees and is continuously updated to show your track over the ground. This is a more useful value than heading, since it includes the wind drift and allows you to verify you're moving in the correct direction towards the next waypoint. The bearing to a waypoint is also continuously updated and represents the desired track from your current position to the next waypoint. You can look at the difference between the track and heading and the true airspeed and the ground speed for an indication of the wind. Track is one of the more important parameters the GPS navigator provides, and most pilots select track as one of the items of information that is always on the screen. Another important element is bearing to the selected waypoint. If you fly a heading that matches the track and the bearing, you'll stay on course. Desired track is just as useful. That is the track from the last waypoint to the next waypoint, or from the point where you selected direct to the next waypoint. If, for example, you wander off a little, the bearing to the next waypoint won't be the same as the desired track. The 650 can also display cross-track error, which is the distance in miles the aircraft is off course in either direction. You can also choose to display GPS-derived altitude here. This will not be as accurate as the altitude displayed on the altimeter, but can serve as a basic backup when all else fails. There are always more options than there are display spaces, so you have to decide what you want to see. The manual for the navigator will tell you how to configure the various screens through a menu page. You can also view these data fields in the corners of the map screen and configure them based on your preferences. If you're lucky enough to fly with more than one navigator, you might want to configure each differently so that most all information is in view all the time. The map screen displays your current position and depicts the active flight plan leg with a magenta line and the upcoming legs in white. You can use the touch screen to pan around the map and tap on an airport or waypoint to call up the details. The database contains information on frequencies, runways, approaches, and more. Back on the home screen, tap the Procedures button to select a departure or arrival procedure or an instrument approach. All the procedures, in other words. The interface is very intuitive and will guide you through selecting the approach type, entry method, and whether you want to load it into the flight plan or activate it. You can even select a waypoint and enter details for a holding pattern if assigned by ATC, including a specified course and leg length. Steering information for the navigator is displayed on the default navigation screen, and on an installation with navigational approval, it is also displayed on the airplane's CDI, HSI, or PFD. Use the CDI button to select what is displayed on the CDI, HSI, or PFD, traditional VOR localizer signal, or GPS. It's the pilot's responsibility to have the correct information selected for viewing. The ideal use of a GPS navigator comes when you enter and activate a flight plan. Fly the route as filed, including a departure procedure if applicable. Select and fly the arrival procedure, and finally, selecting and executing the instrument approach. The navigator would automatically sequence from waypoint to waypoint, and if coupled to a good autopilot, it would take you all the way to your destination. You can access the flight plan screen from the dedicated button on the home screen.
It's important to go beyond basic flight plan entry and use. You need to be good at modifying a flight plan as you go along and jumping ahead to future waypoints if the controller lets you go in a more direct fashion. Or the plan might change because of wind, weather, mechanical, or personal reasons, dictating a change in the GPS selection.
The 650 includes a function that shows the nearest airports, intersections, nav aids, user waypoints, airspace, and some useful frequencies. These can be very handy for situational awareness and in an emergency.
That wraps up our introduction to the Global Navigation Satellite System and en route GPS operations. We'll take a look at GPS approaches in Volume 3.
Out transponder. The transponder is a simple device to use. All we have to do is set in a 4-digit number, which is assigned by ATC for identification purposes. For example, the ATC computer recognizes code 0446 as Cessna 536 Sierra Papa, but the technology behind the transponder has changed over time, and some new features make it more than just a tool for air traffic control. Transponders were used under the name IFF for identification friend or foe in World War II. If the transponder didn't give the right answer, you were literally under the gun. Some colorful language from those days carries on today. The IFF or transponder was known as a parrot, thus the current SWAC terminology. The transponder has an ident feature. When the controller says SWAC ident, and we do, it identifies the target on the scope. Before the current system with discrete codes and data blocks, all the controllers had were targets, and positive radar identification was always made with a SWAC ident. It is still used sometimes when a controller wants to double check on the identification of a target or when there are computer problems. In the late 1980s, transponders began to add mode C, which transmits the airplane's altitude in addition to position. The latest advancement is automatic dependent surveillance broadcast, or ADSB. This system has two parts, ADSB out and ADSB in. ADSB out avionics are essentially more advanced transponders that send out additional information, including your aircraft's track and speed. Most importantly, ADSB transmitters Do not wait for ATC radar to interrogate them before they reply. Instead, they are continually transmitting to anyone and everyone, including a network of ground stations that feed that information back to ATC. There are some important requirements that come along with ADS-B out. It is required inside Class A, B, and C airspace, as well as within 30 nautical miles of Class B and the space above all Class C areas. The equipment is also required at or above 10,000 feet MSL, excluding the airspace within 2,500 feet above ground level. Also note that an ADS-B out transponder must be paired to an approved position source, which essentially means WASP GPS. It's even a good idea to leave your transponder on while taxiing, since larger airports use it to track your location on the runways and taxiways to prevent runway incursions. Transponders and altitude reporting equipment must have been tested by a certified repair station within the preceding 24 calendar months. Transponders are the out part of the system. The other part is ADS-B in, the data link service that provides subscription-free weather and traffic to pilots. If you have an ADS-B in receiver, either portable or installed in the panel, you can view in-flight radar, text weather reports, and nearby traffic. There is a critical detail to remember here. Unlike the weather data, which is broadcast continuously, traffic is only transmitted in response to an ADS-B out message. Note that ADS-B traffic is different from traffic collision avoidance systems or TPAs. These are installed on all airlines and which and similar devices are available in smaller general aviation. These systems actively interrogate the transponders on nearby aircraft regardless of radar coverage or ADS-B ground stations, and display the relative position and altitude of traffic. The most sophisticated versions will command and coordinate evasive maneuvers to avoid conflicts.
Correct. A VOT is ATS route, or Air Traffic Services route, is a generic term which includes the 4 different sets of airlines in the United States, as well as arrival and departure routes. Victor Airways go from 1,200 feet AGL up to, but not including 18,000 feet MSL. Practically, the highest assigned altitude available on Victor Airways is 17,000 feet. Victor Airways are also referred to as VOR Federal Airways. High-altitude airways, called jet routes, start at 18,000 feet MSL and extend up to and include flight level 450. Aircraft above flight level 450 navigate by pointing or direct navigation. Published RNAV codes are found on both the high and low altitude charts. They are magnetic reference routes are found on the high altitude charts. T routes are low altitude RNAV routes, generally established for transition around busy terminal airspace. T routes have also been created as supplements to existing ATS routes and as replacements for other ATS routes when underlying airways have been decontrolled. Finally, there are still common airways in use in coastal North Carolina and Alaska based on low-medium frequency nav aids. Low-medium frequency airways are named for one of 4 colors: red, green, amber, or blue, given a number. Airways are 8 nautical miles wide, 4 on either side of the center line. The airspace is protected, and obstacle clearance from 1,000 feet in non-nautical areas and 2,000 feet in designated nautical areas is assured within the confines of the area. We fly with VOR airplanes that show angular elevation. From a full-scale deflection of the CDI equals 10 degrees off the selected course. We don't have a distance from the center line. We're selecting the course from the V1 is a bit offset, but it can be calculated. 1 degree deflection of the CDI 60 miles from the station equals 1 mile off the airway center. A 10 degree or full-scale deflection of the CDI at 60 miles equals 10 miles off the airway center. 30 miles from the station. A CDI needle deflection of 1 degree equals a half mile. Therefore, a half standard or 5 degree CDI needle deflection 30 miles from the station means that the wind is 2.5 miles off the airway side. When navigating with GPS or other area navigation, the deviation is normally linear, not angular. The sensitivity increases when using GPS in the terminal area and for approaches. In this environment, the deviation may be angular at times. We'll discuss this further in a later volume. Let's take a look at the VORs used for airplanes a bit more closely. Since we're dealing with the direction feature of VORs, vortex, and VOR domains, we'll call them all VORs. VORs used for airways have approximately the same power output, but they are classed as low and high VORs. The usable range depends on aircraft altitude, class of VOR, terrain conditions, and other factors. The FAA provides a standard service volume range for each class of VOR. The standard service volume is a planning range for flights between VORs when not flying on a published airway. Published routes may have cycles beyond the standard service volume for VOR, but these will have been flight checked and approved by the FAA. In flight, you may be able to receive and identify other stations with a strong and steady signal beyond their standard service volume distance. If you're at least 1,000 feet above the VOR station and there is no intervening terrain, you should receive en route VORs at least 40 miles away. VORs classed as low have a standard service volume of 40 nautical miles and are used only for the low altitude or Victor Airways. HVORs are used for both the Victor Airways and JetBlue and have a service volume of as much as 130 nautical miles at altitudes between 18,000 feet and 45,000 feet MSL. However, up to 14,500 feet MSL, the standard range for an HVOR is also 40 nautical miles. Between 14,500 and 17,999 feet MSL, the service volume for high VORs extends to 100 miles. Above 45,000 feet and up to 60,000 feet, this value is also 100 miles. Most pilots using GPS for en route navigation. The FAA is in the process of reducing the number of operational VOR stations across the U.S. To ensure reliable navigation coverage and prevent the GPS becomes unavailable, you need to use VOR for navigation. The FAA has added 2 new VOR classifications, VOR low and VOR high. The service volumes are similar to the original low and high VOR, but guarantee additional reception out to 70 nautical miles, starting at 5,000 feet MSL. One of the reasons for the high low classification is that there are only new frequencies available for all VORs in the low 48 United States. It would thus be impossible to detect all of the frequency interference at higher altitudes. All this is a good reason to always identify the station, since each frequency is used many times throughout the country. Above and beyond certain altitude and distance limits, it's possible to simultaneously receive 2 VORs which have the same frequency. This can usually be recognized by an aural squeal and oscillation of the indicators. Airways are flight checked initially and on a recurring basis. Assures that there is no interference caused by another station. The third class of VOR is called a terminal VOR. Both Jefferson and FAA altitude and route charts identify the terminal VORs. These VORs are usually located on or near airports